In today's video, I'm going to teach you a very simple and easy method that allows anyone to calculate Earth's radius using only a sunset. If for some reason you don't already know, the Earth is essentially a rotating sphere, turning a full 360 degrees in a day, which leads to everywhere experiencing a sunset once per day. For this experiment, you're going to be observing a sunset from lying down and then quickly standing up to be able to see the sun again before watching it set for a second time. The time between these two sunset events and your height is all you need to then find a good approximation of Earth's radius. If this doesn't make immediate sense, don't worry, as I'll explain it using a diagram later, but overall it's a very simple setup. So I'd recommend taking a stopwatch or your phone to a good place where you can observe a sunset in order to accurately time between sunsets, remembering that the sun sets in the west, and for the best results you want to be as close to sea level as possible. So going to a west-facing beach will be the most accurate place to take these observations. Obviously, when you're taking observations, don't stare directly at the sun, as it is a blazing hot fireball that will damage your eyes. So wear sunglasses or look away from the actual sun. You only need to be able to tell when the sun is set completely. You don't need to look directly at it. Now on to the derivation as to how these observations will actually allow us to calculate Earth's radius. I'm going to start by drawing the Earth as a circle, with arrows indicating it rotating anti-clockwise on its axis as seen from the North Pole. Next I'll draw the Sun, a little bit away from the Earth in the diagram. Of course this diagram is not to scale. If it were, the Sun would be much bigger, and if it were that close, we'd all be fried from its incredible heat or choked up by its crippling radiation. Anyway, I've added on two rays from the Sun. The top one represents the place on Earth currently experiencing a sunset, as an observer from that point would only just be seeing the sun dip below their horizon. Conversely, the bottom spot is where a sunrise would be taking place, which to be fair could also be used for this experiment, but would require lots of standing around waiting for the exact moment the sun rises, then sitting to watch it again, so it's far more tedious than using a sunset. But be my guest to try it this way instead. As soon as our observer at the top sees the sunset, they stand up and time how long before they see the sun set again. This spot is shown by the stick with a dot on it, and is a small ways left of the original spot on the diagram, as Earth will have rotated a small angle theta in that time. Now I've marked on Earth's centre and joined up between the centre and these 2 points of interest. Using a circle theorem that tangents meet radii at right angles, you can see that a beautiful right angle triangle appears in the diagram, with the prior mentioned angle theta between the 2 points and the Earth's centre. Here I've labelled Earth's radius little r and the observer's height little h. Using simple trigonometry, I can write the cosine of theta as r divided by r plus h. Also, being a physicist, I rewrite cosine theta using a small angle approximation, which is fine here as theta will be very small, as the time between the two sunsets is short. Just for clarity, point 1 is the first sunset location where they're lying down, and point 2 is the location of the second sunset once they've stood up, and you can see the Earth has turned by the small angle theta in that time. Theta must therefore be equal to Earth's angular speed omega multiplied by the time between sunsets, which I've called t. This model of course isn't perfect, as you do need to be at sea level, and even then has its flaws, since in reality Earth isn't a perfect sphere. However, as you'll see later, this model does give reasonable predictions for Earth's radius, so let's stick with it for now. Anyway, omega is easy to work out. As we know, Earth turns a full rotation, 360 degrees or 2 pi radians in one day. Since there are 86,400 seconds in a day, we can now know omega as 2 pi divided by 86,400 radians per second. This does mean we are now stuck with using seconds as our time measurement unit, but that's fine. Now I'm going to solve for r in terms of t and h by rearranging the equations I've just derived, so feel free to skip on ahead if this algebra doesn't appeal to you. So first I equate the small angle approximation of cos theta to the corresponding triangular lengths. Multiplying up by r plus h and simplifying yields an equation in terms of r theta and h. That is, r equals h lots of 2 divided by theta squared minus 1. Now I'll sub in what theta was using the definition of Earth's rotation speed and the time taken. So theta squared is also equal to 2 pi t divided by 86,400 all squared. Subbing this in and simplifying gives the final expression we can use to find Earth's radius. Finally, I'll simplify the constant terms to one big constant with units of seconds squared, and I'll give it to 2 significant figures, and that seems to be a reasonable accuracy for this model. So our final expression is the radius of the Earth r equals 3.8 times 10 to the 8 seconds squared multiplied by the observer's height h divided by the time between sunsets t squared. There are some further points to consider regarding this method. First off is a discrepancy in the height. For all intents and purposes, using your physical height as the value of h is a good approximation. However, in reality, h will be smaller. You have to remember that even when lying prone or crouched down observing a sunset, your eyes won't be exactly on the ground, unless of course you burrow a hole to sit in where your eyes are perfectly at sea level, although this isn't necessary or recommended. Also, when you're stood up, your eyes aren't at the very top of your body, leading to your height being an overestimate of the true height difference between sunset events. This shouldn't be anything to worry about though, since it's most likely you can't observe perfectly at sea level, and as you'll see when I mention my results and repeats at different altitudes, the effects of being a few tens of meters above sea level isn't a huge source of error, but it is worth being aware of in any error analysis. There are alterations to the model and equation one can do to take into account these height discrepancies, such as by using multiple triangles with our hypotenuses at different heights. However, in my opinion, this isn't needed in order to get reasonable values for Earth's radius, and so I haven't bothered in my model. You may now be thinking that with all these assumptions and approximations, that the value you get for Earth's radius won't be accurate or precise, yet you would be surprised. Recall that all these assumptions and approximations are reasonable and have tiny changes on the overall setup. By this I mean the radius of the Earth is so massive in comparison to your height, or the difference between the cosine and the small angle approximation in the angles considered, that even with these approximations the values you get are reasonable and the model is good. Now let's talk about processing your results. By now you should have found the time between your sunsets and also know how tall you are in meters. So to find your predicted value of Earth's radius, you just need to plug it into the equation that I derived earlier. That being r equals 3.8 times 10 to the 8 multiplied by h divided by t squared. Remember, h must be in meters and t in seconds. Using one of my results as an example, I stand at a respectable 179 centimeters and found the time between sunsets to be 4.1 seconds. So here I would plug in h equals 0.179 and t equals 4.1. This wasn't taken at sea level, but gives a radius of Earth as 4 times 10 to the 6 meters, or around 4 million meters to one significant figure. Asking our good friend Google tells us that the true radius is around 6.4 times 10 to the 6 meters, or around 6 million meters. So the value in my example is similar to the true value, being in the same magnitude and reasonable in value. However, something I noticed quite quickly in my results was that all my predicted radii were underestimates of the true value. Since I repeated this experiment at various altitudes to see how altitude affects the accuracy of the model, I found that altitude plays a small role as expected in the final result. I'd still recommend being at sea level though, but finding a place where you can see the horizon below 80-ish meters altitude should give you a reasonable radius. Anyway, back to what I was saying about the underestimates. I always underestimated the Earth's radius at every altitude. This implies a systematic error in my model and experiment. I'm not entirely sure what could cause this error, but my best guess is that it's an atmospheric effect caused by Earth's atmosphere refracting the light from the sun in slightly different ways based on how high you are above sea level. Since the atmosphere refracts the sunlight, it makes the sunset appear slightly later than when the sun has actually set below the horizon. This could explain why I keep guessing underestimates, as it may make an observer see a sunset happen slightly later at slightly higher altitudes, i.e. when they've stood up, thus prolonging the time taken between observed sunsets. This in effect would lower the experimental radius one derives as a result. This is of course just my theory, and could very easily be incorrect, so I'd invite anyone watching with a different idea which explains the consistent underestimates to comment down below their theory. I'd be interested to know. Or perhaps I made some other error in my measurements and other people find overestimates for the radius, or perhaps neither. I'd also be interested to know this if you do try the experiment yourself, so yes, please let me know in the comments. Anyway, there are of course better ways to measure Earth's radius, but most of them require professional expensive equipment, and considering how close I got using this relatively cheap setup, I'm quite pleased with this method. Another cheap way, however, involves looking at shadow length at different places at specific times, such as at the solstices. These are less astronomical and much harder to do, and so probably won't be covered here on my channel, but are nonetheless interesting, and so I would recommend checking these out as well if you want alternate methods. To conclude, I've shown you a simple method which can be used to find Earth's radius to surprising accuracy. This also works as evidence against flat Earth theory, which is of course an added benefit. And so with that, I thank you for watching this short astronomy video.